In this video, one of a series I'm making about the Collatz conjecture, also known as the 3x plus 1 problem, I'm looking at loops as they occur in Collatz-style sequences. And a Collatz-style sequence is one that instead of plus 1 is plus n greater than 1. So a series of numbers, in order to make a loop, has to go up and down by the same amount for that sequence to repeat. And to find such a counterexample for a Collatz-type sequence, we need to look at plus n greater than 1. So 3x plus 11 cycles of input 27. This is just an example. We have a nice looping sequence here that will continue forever, for infinity. And what has happened here is that the output of 27 is 23, the output of 23 is 3, the output of 3 is 5. And then we enter the cycle, which ends in 5 or begins in 5, regardless of how you look at it. So how did this happen? Well, we have two inputs producing the same output, and that is the only way a sequence can occur. So input 3 becomes output 5, and input 31 becomes output 5. This may seem a little strange, but it happens to be the case when you're using plus 11 instead of plus 1. Now the interesting thing to look at, and I'm going to pass over the regular sequences for regular sequences for 3x plus 1, where I'm contrasting an odd-even sequence with an odd-only sequence, and that the results are actually the same, but simpler in the case of the odd-only sequence. What I just want to show you is that in the function that produces this input-output sequence, and again I won't explain how I arrived at it, but you'll notice that I've got x plus n and x minus n. So in another video I use obviously plus 1. Here with plus n I can substitute any odd number and get an input-output table for that number. So here's an input-output table for 3x plus 17. And what I want you to notice here is that we have inverse relationships. 14 minus 14 minus 20, 20. And so where do these come from? They're simply input 11, output 25 is 14, input 13, output minus 1 is minus 14, input 21, output 1 is minus 20, and we're looking at this as a reverse operation. 23, 43 is 20. So these cancel each other out, these inverse operations. They become 0. And notice in the middle we have a 0. So this is highly significant, and I'll say what this 0 means in the next video, but here I just want to illustrate that these differences, plus 14, minus 14, plus 20, minus 20, the contributing numbers, the input-output numbers, aren't actually part of the loop, or not all of them are. However, their differences are part of the loop, minus 14 and minus 20. So that is essentially the reason you get a loop for a sequence where x is greater, where n is greater than 1. And there's a rule here that the inverse pairs are symmetrical between the n input and output, that's the 0 to 0, or the 17 to 17 with the difference of 0. You see that there are two pairs, plus and minus n minus